So we are ready for our last talk about assessing and enhancing machine learning systems integrity. I mean, when you look at a system, you want to understand the integrity. You want to understand if it acts with fairness, if it acts with all ethical issues, and if it is prepared to the real world. And there are ways to assess it and understand it. I think now I'm as an investor, but also users and clients are doing this assessment part of their taking decisions in whether investing or using those systems. And I want to call up to stage Dr. Mahmood Sharif, Senior Lecturer at the Computer Science School at Tel Aviv University. Good luck.
Thank you. Well, thank you for the introduction. Hello everyone. I'm very happy to be here today to tell you about our work on assessing and enhancing machine learning systems integrity in the real world. And the work that I'll tell you about was popularized by the work of Segre et al. About 10 years ago. So even back then, we were able to build models that were very accurate and highly performant. So even if we take this neural network that was proposed about 10 years ago and we use it to classify these models, or these images, excuse me, then it will do good work and tell us that there's a lion, a race car, and traffic lights. Right? Unfortunately, however, it was shown that machine learning-based systems, and deep neural networks in particular, are vulnerable to attacks. So if you see these images, and compare them to the images in the previous slide, then it's hard to see the differences between these and the previous images. However, if you use the same model to classify them, then it's going to tell us that the lion is a pelican, that the race car is a speedboat, and that the traffic light is jeans. Now, this work of Segre et al. Has sparked the research community's interest in a variety of ways. And among others, it has turned the community's attention to developing methods to assess machine learning model susceptibility to attacks. And we want to do this as faithfully as possible, either by considering attacks that produce imperceptible perturbations, like the ones we've seen in the previous slide, or by considering the real-world constraints under which adversaries may need to operate in order to fool a system. Naturally, another major challenge is devising and developing ways in order to enhance the adversarial robustness of machine learning-based systems. So in our lab, we did our fair share of attempts in order to answer these questions. So for example, we developed a technique to more reliably assess the robustness of deep neural networks against imperceptible perturbations like the one that you've seen earlier. We also considered ways to evade machine learning-based systems under real-world constraints. So for example, we considered ways to fool face recognition while changing our physical appearance in a simple or very minor manner. And in fact, an example was shown in Oren's slides earlier, so I could not ask for a better speaker to present before me. Right. We also considered what would happen if we're dealing with attacks against tabular models that considered handcrafted features. And we also considered a bunch of other domains, like, for example, malware detection. We also have several works to defend machine learning-based systems and improve their robustness. Here, for instance, we considered malware detection, and we showed ways to train models to make them harder to fool by adversaries that rewrite binaries in order to evade detection. We also considered machine learning systems that are used to optimize systems that are used for a variety of things, including for optimizing job scheduling in cluster. And there, for example, we showed that it's not possible in certain cases, or we can prove that in certain cases, it's not possible to game the system by, for example, speeding up, or in order to speed up the jobs that you're submitting. In this work, or in this talk, I'd like to highlight one of our recent works on attacking tabular models. This work was led by my student, Matan Bentov, and was in collaboration with Daniel Deutsch and Nave Frost. So machine learning models on tabular data are actually very commonly used still, and they are used in a variety of critical applications. So they are used for malware detection, they are used for medical diagnosis, and they are also used in the financial domain. And the kind of data sets that or data that we're dealing with contains samples where you have feature vectors where each coordinate describes certain property of the input. For example, the age of a person or the loan amount that they are asking for, etc. Now, in this work, we ask the question of how susceptible are tabular models to evasion attacks under real-world constraints. And I'll elaborate. So, as I've alluded to earlier, evasion attacks were first proposed in the image domain, and they were thoroughly explored there. Now, it's well known, I think, to many of us that it's now possible to turn pandas into gibbons. And in fact, the nice properties of the image domain makes it possible to create these attacks relatively easily, including, for example, by using gradient-based search, using algorithms like PGD in order to find what are the perturbations that would lead to misclassification. Now, it turns out also that these effects can relatively easily be realized. For example, in this way. Now, to sum up, in the image domain, we can generically realize attacks or evaluate robustness against realized attacks. Ideally, we want to have the same capability also in the tabular data domain. However, unlike the vision domain, there is a non-trivial gap between the problem space. So for example, here, the space where phishing pages or HTML or phishing pages exist, and the feature space, where we're deriving the properties of the page in order to provide them to the classifier. Now, naively attempting to perturb the input in a similar manner to the image domain would lead to inputs that are nonsensical and cannot be realized. So for example, what does it mean to create a half a mail to, right? Doesn't make sense. It also is unclear how, or what is the meaning of imperceptibility or cost in this domain. So we found that prior work either focused on the problem space, where it created attacks that are specific to particular domains, and it would require lots of human effort in order to adopt these attacks in other domains, or so these line of work lacked genericness, or there was this generic work where it was possible to apply the same technique to various application domains. However, these attacks lack realizability, right? So they don't take real-world constraints into account. And so to address this, we propose CAFA, a system that enables white box robustness evaluation, so when you have access to the model, in a way that, that is done automatically by automatically finding what are the constraints of this domain. And then using a suitable cost measure and by taking into account the properties of the tabular domain, this CAFA attack produces adversarial examples that are suitable in both in generically evaluating robustness against realizable attacks in the tabular domain, as I'll show later. So before diving into the attack itself, I'd like to present two types of data integrity constraints in which, which we may care about. The first one that may affect non-realizability is the structure constraints. So it turns out, for example, that certain features may need to have certain structures. So they may actually need to be binary, right? And so we need to respect these types of constraints in order to create realizable attacks. Another type of constraint is basically interdependencies between features, right? So there is semantic meaning to features, and they are often interdependent. And to model this type of constraints, we use what's called denial constraints, a primitive from databases that is widely used and highly expressive. Now, in a nutshell, a denial constraint is a conjunction of predicates that cannot hold together. And they can be mined using automatic techniques from the training set, and we allow basically soft constraints. So we allow a small rate of violation. Now, with these types of constraints, we can define our attack. So CAFA is an attack that has two stages. It starts by an offline stage where it defines the constraints or finds them. And this basically, in the first stage, we define what are the structural constraints by investigating what's the structure of the data. And then we mine the denial constraints that basically define the inter-feature relationships. After this is done, we can, given a sample, we can provide it to an attack that would, given a neural network, perturb the sample in a way that takes the structural constraints into account so that these are not violated. And this attack also considers a variant of what's called the Carlini-Wagner attack in order to minimize the number of changes that are applied to the input so that it would be easier and to realize the attack with lower cost. Right? This would give us a sample that satisfies the required structure and is misclassified typically. However, the sample may violate the denial constraints. So it might violate some inter-feature or cross-feature relationships. And so to satisfy these, we use a SAT solver to project the sample on the denial constraints that we mined earlier. And this would give us the adversarial example that would be hopefully also realizable and misclassified at the same time. We evaluated this attack on 3 different data sets, targeting 2 types of popular models, MLPs and tabnets. And we compared the attacks on several axes, or over several axes. First, we measured the quality of the constraints that we mined. And we did this in terms of completeness and soundness. And you can consider this as basically being analogous to recall and precision. And we cared about the balance between these. So wanted to have essentially a high harmonic mean for both of these quantities. Now, compared to previous types of constraints, it turns out that and according to the way they were built, they had high completeness, but they lacked soundness. In contrast, denial constraints had higher completeness, or had not as high completeness, but had significantly higher soundness and much higher harmonic mean. And in fact, it could achieve this with much fewer constraints, meaning that it would enable much more efficient attacks. We evaluated the attacks in terms of both success rate and cost. And for success rate, essentially, we wanted as many adversarial examples to be misclassified, and this is now going to be shown in terms of the size of the bubbles that you will see. We also cared about cost. We wanted to minimize as few, or perturb as few features as possible, as little as possible. And so we wanted essentially, better results on this graph lie in the top or in the bottom left corner. You could see that Kappa did much better than earlier attacks. We also took excuse me, I'm a bit confused about what you're saying and what I'm saying, so the slides might be a bit behind. And we also took a problem space perspective at this problem and tested whether the attacks that we could create with Kappa could also be realized much more successfully. To do this, we examined the phishing domain as a case study, and we attempted to realize adversarial examples manually after running the attack. Turns out that not considering constraints whatsoever would lead to evasive samples that cannot be implemented in the problem space, right? So this does not tell us anything about how robust this system is really in practice. If we take previous constraints into account, turns out that once we do the projection, many of the samples would no longer be evasive. Now, Kappa, on the other hand, was able to create much more evasive samples that are also realizable. And still, there is a gap for improvement. And this is something that we'll leave for future work, because it turns out that even denial constraints, while being expressive, can be further improved to better model the feature space and the relationships between features. So to conclude, as seen by our POS system Kappa, generic feature space attacks can be more realizable using database integrity techniques. Still, attacking models in the tabular domain in generic manner still poses challenge relatively to the fairly easy image domain. But here we can hope that by developing better constraint mining techniques, we would also be able to improve our ability to evaluate the robustness of models more faithfully. So our code is public. Our paper is also available online. So if you're interested, I invite you to read them. And thank you very much for listening.
Thank you very much. Thank you. I'll take that. We don't have time for questions, so if someone wants, they're going to catch you later. I think that's all about AI and cyber. I think tomorrow we have cyber and AI, or the other way around, whatever you like. With Yaniv, he's sitting here waiting. But all of that was only a warm-up show, right? Because the next stage, the next session is probably the most interesting one. We have their piano or whatever it is, and something behind the curtain. So it's going to be something very interesting about the future of creativity in the generative AI era. And for moderating this session and leading you through, I'm pleased to call Eyal Brook to the stage. I wish you all a pleasant evening and enjoy the rest of the conference. Thank you very much.